All right, let's talk about one of the absolute beasts inside modern computers, the GPU. You've probably heard that term thrown around a lot, right? Graphics processing unit. But what you might not know is that its real superpower goes way beyond just making your games look pretty. So, let's get into it. Have you ever wondered why your games need a really powerful graphics card? If you've ever built a PC or even just looked at the specs for a new laptop, you know the GPU is always this huge selling point. So why? What makes this one piece of hardware so essential for those buttery smooth frame rates and incredible visuals? The answer? Well, it's pretty fascinating. Because you see, that graphics card isn't really just for graphics anymore. It's the computer's secret weapon. It's parallel muscle, if you will. And it's designed to do one thing unbelievably well: tackle thousands, even millions, of little tasks all at the exact same time. And to really get how it works, we need a good analogy. So let's frame this as a classic showdown. One brilliant genius versus a massive, perfectly coordinated army. This is, at its heart, the fundamental difference between your computer's main brain, the CPU, and its specialized workhorse, the GPU. Okay, so picture this. Your CPU, that's like a world-class expert chef in a Michelin star kitchen. This chef is a total genius, right? They can juggle a bunch of really complex, different tasks one after the other. They can whip up a souffle, butcher a fish, invent a whole new dish on the spot. But the GPU, that's completely different. It's an army of, say, 10,000 line cooks. Now, these cooks, they aren't creative geniuses. They can't invent a new recipe. But if you give them one simple command like, chop this onion, you get 10,000 onions chopped perfectly, and you get it done all at the exact same time. See the difference? And this whole chef versus army thing isn't just a cute story. It's literally reflected in the hardware itself. A CPU has just a handful of very complex, very powerful cores. Those are our genius chefs. They're amazing at sequential tasks, things that have to happen in order, like running your operating system. The GPU, on the other hand, has thousands of much simpler cores, our army of line cooks, and their one big strength is parallel math, which is exactly what you need for crazy demanding stuff like gaming and AI. Okay, so we've established the GPU is an army, but how do you actually organize an army like that to be so ridiculously effective? How do you get thousands of tiny little processors to all work together without just creating total chaos? Well, the architecture is actually brilliantly simple. First, let's just take a second to appreciate the sheer scale we're talking about here. We're not talking about 4 or 8 or even 16 cores like you'd find in a high-end CPU. A powerful modern GPU can have over 10,000 of them. The number is just staggering, and that's really the foundation of all its power. Now, what's crucial to understand is that each one of these thousands of cores isn't a little genius. No, they're incredibly simple and super efficient. They are built for one thing: repetition, doing the same calculation over and over and over again, in perfect lockstep with all of their neighbors. This design makes them the absolute perfect tool for the massive repetitive math that things like graphics and AI are built on. There's actually a super nerdy official name for this whole process, and it's called SIMD. It stands for Single Instruction, Multiple Data. And honestly, it's the perfect description. It's just like our kitchen analogy. The head chef yells out one single instruction: hey, calculate the color for this one pixel. And then thousands of those line cook cores go and execute that exact same command, but on multiple pieces of data, meaning thousands of different pixels all at the same time. One command, thousands of results. That's the magic right there. So we've kind of got the how down. Now let's get to the why. Why does this kind of parallel power matter so much today? Well, it's because the biggest, most complex problems we're trying to solve right now, from creating photorealistic game worlds to building artificial intelligence, are all at their core parallel problems. Just think about it for a second. Rendering a 4K game screen means you have to calculate the color, the light, the shadow for over 8 million pixels, and you have to do it 60 times every single second. That is a perfect job for our army of line cooks. And the same logic applies to training an AI model, which is basically just doing millions and millions of simple math operations. A CPU would absolutely choke on that workload, but for a GPU, hey, it's just another Tuesday. And the difference in performance isn't just a little bit. We are talking about trillions of calculations every single second. If you tried to force a CPU's few genius chef cores to do that kind of work, you'd create a massive bottleneck. The whole system would just grind to a halt. The GPU, it just unleashes all that computational power.
So if there's one big idea to take away from all of this, it's this. Whenever you have a huge, massive problem that can be broken down into thousands of smaller, identical problems, like coloring pixels or training an AI, the GPU isn't just a good tool for the job, it is the perfect tool for the job.
Okay, but that brings up a really interesting question, doesn't it? GPUs are absolute monsters for training these giant AI models in some huge data center, but they're also super power hungry. So what happens when you want to run that same AI, but you want to do it efficiently on something small, something you hold in your hand, like your phone? Well, for that job, a totally new kind of processor is starting to take center stage. And we're going to talk all about that next time when we dive into the NPU.